The mic, Amasika, closely. Yeah, it's off. Yanzu. Okay.
Good morning, everyone, and welcome to our first and third section of long overdue workshop. As a host and somebody who is at the center of this program, I would like to welcome all the participants for taking their time to honor this workshop. Okay. This program, we have been updating this program because initially we already sent the online survey. So we have to use, there is need to use the survey tailored the needs of the participant. So my presentation will cover what is on the slides, from production and activities to well-known theoretical equation, Wahel, back and forth theorem, one and sham, then exchange correlations, and what DFT do and what is the limitation, zero DFT calculation. As I have mentioned that this is a way that define the program of this workshop. This is an updated survey of about 20 participants. So based on this participant, we agree that most of our participants are new in DFT. So with some of them that have some experience and already used and are using the code. So we decided to limit it, the whole workshop today, basics of the DFT. So this is the survey. If you look at it, the red A, sorry, the green, you see the first question, the green is A. And A is an option that says I have parts of DFT, but have little to no practical experience. So as you can see, the percentage. Question 2, the high response we have, what is your primary goal for this training? Select any two options, and that option A, B, C, D, E, F, and G. That G option actually is all of them, all of the options. So if you look at the first one, is to learn about the mental theory behind the DFT. Okay. So if you check all these, what we have in the let's just sample. What is your experience counting espresso? Question 4. The first option is I have no experience with counting Espresso. So you can see we have to agree that most of our personnel here they are. Okay, so I am not going to spend much time. Let's look at the last one. What is your area of specialization? And we have the A option that says computational condensed matter phase. So we agree that most of us here are background in computation master thesis. Either they are starting or they have already into it fully. It's actually very, very difficult to try to introduce the concept of DFT in 1 hour. But my belief is that after this, I am going to give you a good overview and also the philosophy behind the basic function theory. It's actually a very wide subject. Okay? So if we the philosophy, that will help us understand the mathematical expression that represent the philosophy of DFT or of quantum mechanics. This is the most of the difficulty we have. My little experience interacting with students using DFT, this is what it's like to understand the philosophy behind the subject. I will start with Bloch theorem. This is well-known theorem, and it is, I can say, the background or the linkage between solid-state physics and density functional theory. That equation, A, B is equal to 2 phi chromical delta Ij. I will be referring to these slides. It actually is a primitive lattice vectors. B is the primitive lattice of the real of the unit cell. Okay, so and we know that in solids we have crystals and amorphous. Crystal is periodic in nature. So, and if you want to define or understand the behavior of electrons in the lattice, so it's given by that expression psi of k is equal to that exponential actually is a simple wave multiplied by the periodic functions. I say that I will keep going on back on this slide. This is just an overview. But we know that condensed matter Hamiltonian is given by that Schrodinger equation psi h of psi, where h is our Hamiltonian, and that Hamiltonian is potential and the kinetic energy of the systems. Okay, so we have kinetic energy operator and the potential energy. But we know also that in solids, solid contain about 10 to the power of 23 atoms or more. So if you imagine trying to understand electron propagation in the atoms, you imagine how it would be. Okay. So this condensed matter Hamiltonian actually contain about 5 terms. The first one we say is kinetic energy operator of the nuclei, then the kinetic energy operator of the electron. Then the rest three terms are Coulomb potential, one due to interaction between electrons and electrons, and two due to the interaction between electrons and nuclei, three due to interaction of nuclei and other nuclei. Right? So we have what we call Oppenheimer approximation. The first approximation in DFT will tell you that if you compare the nuclei and electron, nuclei is more than 2,000 times heavier than electron. So it's good to disregard the effect of the nuclei when you are trying to solve a Schrodinger equation for many body system. Hence, the condensed matter Hamiltonian will have now just three terms: kinetic energy of electron, then electron, Coulomb potential of electron and other electrons, and Coulomb potential of electron and the nuclei. Okay, so one Oppenheimer, that's rate, we say, okay, we don't need that kinetic energy of electron, so the term goes. So from many body to one body problem, this is what we will be seeing. It's one of the clever assumptions to solve. Apart from harnessing the periodicity of the system, so we say that if you have a system, let's say a hydrogen, just one proton, it has just one electron. Electron in three dimensions, we have the wave function that you end up having a matrix of three-dimensional matrix, right? If you have two electron system, you have a matrix that is having 6. If you have 3, you have 9 by 9 matrix. So imagine when you have a lot of atoms in your system, almost infinite number of electrons, let's say 10 to the power 100. How do you imagine to handle a matrix of 100 by 100? So this is one of the clever things that if you want to determine electron density, then it means you are going to be looking at a calculation for a system that cannot be solved in real time. So the clever assumption is that it's by Horn Sham that they introduce what they call electric potential of non-interacting electron. So if you have non-interacting electron, you end up converting a 3n problem to 1 3n problem because the electron are not interacting, right? Okay, so you end up having a electron density, downstate electron density as a summation of individual non-interacting particle or electrons. Okay, so then propose a very clever assumption that all ground-state properties of the quantum system are uniquely defined by the ground-state electron density. So there is one-to-one correspondence. If you want to know the ground-state energy of the system, just look at the ground-state electron density. But however, this proposal they made in 1964 is just like they proposed a functional, an exact functional that doesn't have a solution. So it was later after this 1994 that Kohn and Sham now proposed what they call a clever trick. In fact, that clever trick was what earned them a Nobel Prize. Okay, so what he proposed actually is what we call conjunct effective potential that contain three graphs. Contain external potential. This external potential actually it is the physical real landscape where you have nuclei that pull the electron inside the atomic landscape. And the second one actually is Hartree-Fock potential, which is also kind of Coulomb interaction that consider correlation. I'm going to talk about correlation and exchange later on. And the last term proposed actually is what we call exchange and potential. And that is where the whole quantum mechanics of density function theory lies. Whatever is happening is trying to appropriate this external potential. And we are going to know or understand what actually is that external correlation. Okay? They call it quantum willingness. So this is part of what I have just mentioned, that atomic landscape is repeating, hence positively charged nuclei of photon create a periodic landscape of hills and valleys, which are the electric potentials. And the question is that how this quantum electron will behave in this never-ending landscape, never-ending repeating landscape. So electron wave function in a periodic crystal can be written as a plane wave multiplied by periodic function, which is the relationship I have just mentioned before. So in reality, the wave function is not periodic, cannot be periodic. That's a trick they do to address that problem. So this quotient effective potential I mentioned before actually is the exchange potential, which is physical landscape, a deep pit created by a nucleus at the center, pulling the electrons, and there are Hartree potential and exchange and correlation. Okay, exchange and correlation. I decided to give a small analogy. Okay, it is suppose that you want to predict the noise in Hill library. The noise, if you want to go exact, then you have to track all the people inside that library. If you want to, right? This is if you want to get the correct information. So to know the exact noise, you have to track every single person. And are they whispering? Are they moving chairs? Because it's part of noise. Are they avoiding noisy person in the corner? Are they brainstorming together? Are they brainstorming together? This is the real complex problem of electrons. We call it electron social behavior. So if you are asked to do that, you can imagine to get this minute detail. Okay? So DFT is clever to say, okay, a clever idea is that forget about writing individuals, just focus, we just need to know the density of people in each room. If you can get the density of people in each room, then that should be enough to calculate the overall noise level inside the library. But that's very far approximation, right? Okay. However, people density doesn't automatically tell you about the social rule. The social rule that actually create the noise. That these rules are the external effects. One, it's just impossible to have two people on the same chair. That's the external effect. It's the rule of the land, right? You cannot have two people. So two people sit in the exact same chair at the same time. This isn't a boundary function. It's just a fundamental rule of, let's say, kill library. So for our news participant, kill is Hashim Ibrahim library will be happier than you. Okay? So this rule creates a kind of order people naturally space out. This is what we call Pauli exclusion principle. Okay? Then the correlation effect. The correlation, people adjust their behavior based on others. You don't sit right next to a stranger if there are other pre-seats, right? You whisper if someone is reading there. All are just control of the noise level. You are fast through the library actually correlate with everyone else. You cannot look anyhow. Try to avoid colliding with their. These are what we call correlation effect. But the exact rule nobody knows. So the physicists have created different approximate rules. So what I'm saying in Russian is that of all the little I have mentioned the real quantum mechanism is on the action and correlation potential, but approximation the rule is actually not possible because one, okay, so what I'm saying for the interruption was so we say now what we need to understand is an approximation. How are we going to do this approximation? The first approximation is the example I gave. We just try to understand the noise level each room and just sum it, and maybe you can predict the noise of that level, which is a very far approximation. This is what we call LDA. So LDA just approximating the actual correlation point. That's how electrons interact with itself. So the LDA, the simplest rule book, it assumes the rule in the crowd room are the same. So it assumes the rules in the crowded room are the same as the rule in slightly crowded room. So you can see how bad this approximation is. GGA is smarter rule book. It doesn't just look at how many people are in the room, but also how the crowd density changes. So if you have a density, now you just need to integrate potential density. That will tell you the denser, why you have the denser noise and why you don't have. Okay. In a more complex situation, these are like ultra detailed rule book that even account for if the two people are friends, how the pitch of their noise. You understand? Okay, they might be talk a little louder. And the more detail is even going to say, okay, what makes them to be friends? So it goes on. So what all this are implying is they are trying to find the final answer to the solution of original equation. So if you have a system, you look at your system, then you know which function are you going to use, which approximation are you going to use. Okay, this is what I said actually a brief philosophy about this what we do when we talk about effective potential and also distance and correlation potential. Okay, so let me go back. Okay, so we know that when we talk about line foundation, we talk about fundamental property of waves, periodic structure. That a perfect crystal. What is a crystal? In solid state, okay, when we say a crystal structure, actually what comes to mind as a computational scientist is one, you have a unit cell that's defined by 3, 1, leading to 7 crystal systems. These are the normal 7 crystal system we have. We have from triclinic, no symmetry, monoclinic, orthorhombic, or tetragonal 2, cubic 3, trigonal, and hexagonal. These numbers here are what we call light centered. For example, if you look at cubic, you say a cubic structure exists in either primitive lattice, no centered, or a body-centered cubic, or a face-centered cubic. Okay, so that's this 3. And we know that a cubic actually is the highest symmetric structure you can have. So it has 3 right angles. For example, what is 4 ball here? When you have a rotation around 2π over 2/4, 90 around a specific axis, you rotate and still the crystal lattice is unchanged. Then we say that particular crystal structure has 4 ball. When it's a 4 ball from plus 3-fold, then it means you have double rotation and still it maintains. That's why highly symmetric structure you can have. Okay, then we have parameters like this, which are 14, atomic basis, symmetries, stealth proof, Woodland cell, reciprocal lattice William zone. So if you are doing DFT, these are actually basics of solid state physics. You need to know the system you are handling, because I'm going to talk about errors in DFT. But really, there are so many mistakes we are doing. When you are studying a system, you need to really understand about the system you are, your own system. Okay? So we have electronic structure, periodic boundary condition, Roche theorem, Schrödinger equation. This is what I have said. So, question here. Now, what can you say about the point proof system? Now, there is actually a website that will contain all this information. You have a system, whatever it is, you can just go to the website and you check all the information on the particular system of interest. If your system, maybe a small digression, some code are not symmetry sensitive. That's why sometimes if you are using code, you need to understand exactly what you are doing. If you create this, you have a static system, you maybe tend to introduce some impurities, then definitely the information, all this information I talk about will change. Sorry.
kake so kai gaba ko baya bayan kake bayan kake
Okay. Now that being said, I think I have some. Okay. So now, I mentioned that according to Avogadro, for a small volume, there are atoms in the order of 10 to the power 23. Therefore, there is necessity to reduce the problem to achieve a numerical solution. So, Schrodinger equation can be applied to determine the property of a solid crystal quantitatively. I believe because we are all physics-based, we know what Schrodinger equation is. Actually, it's a quantum mechanics equation that we can use to understand the behavior of some atomic particles. Okay, so however, it's very difficult, or even impossible to be solved for many body systems. Therefore, you need to do approximation. So, I just want to take us back a little bit in the history. We know that in 1900s, Planck published this paper about quantization flow of emission, which is actually a turning point for understanding of quanta that lie the groundwork of quantum theory. This is almost more than 100 years. Then early development of control structure theory was in 1920. Then also in 1923, we have publication of Rogli, Web and Quanta. Later on, publication that laid the foundation of web mechanics theories by Schrodinger in 1925. Then 26, full paper on quantum mechanics by Paul Dirac. Then later on, 1928, Felix Bloch published his paper, The Quantum Mechanics of Electron Crystals. So later on, so many improvement on trying to understand the behavior of some atomic particles. Okay, so a unit cell, as I mentioned, the crystal structure in the reciprocal space, that is a post-Brillouin zone, is defined by three lattice vectors leading to seven crystal system, photon rubber lattice, and atomic basis. Now, in density functional theory, which is the most computational, in DFT, most of the computations are represented in post-Brillouin zone. It's analogous to 3D physical space, and the lattice vector in cases are selected so that they are orthogonal to vectors in real space. Now, to calculate the properties, won't be possible because all particle content in the system will have to be considered. This results in a equation that cannot be solved in finite time, but infinite problem can be reduced to small number of atoms due to the celestial symmetry. Okay, so the equation I have mentioned, where you have A dot B is equal to 2 phi delta. That A, as I said, is actually the perimeter lattice vector in real space. P in local lattice vector, where delta actually, as we know, is spherical delta, which can be 1. If it's 1, you have A dot B to be 90 perpendicular, two vectors are perpendicular. So we have a real space lattice A pointing along the x direction of crystal and is orthogonal to the different reciprocal lattice vector B. Their dot product then is 0. When you have normalized case where you have 1, you have the dot product of the real vector and its corresponding reciprocal partner is exactly 2 phi. Now, why is this the cornerstone of Bloch theorem? Is that the reciprocal lattice vector B define all possible wave levels, that is crystal momenta, that are unique for the electron in that particular crystal. Therefore, the condition A dot B is equal to phi ensures that a Bloch wave with a wave vector K and one of the wave vector is K plus B are physically identical inside the crystal. Therefore, this is why electron crystal need to be studied only within the first Lorentz zone. So this is just what I have finished talking about. Then for a whole lattice vector K, we have a wave function is equal to wave of K plus K. This implies that in order to describe a crystal system, what is the wave function for the wave vector inside the Bello is needed. Now, electronic structure need a quantum treatment, and the main scheme is density functional theory. And the challenge is for many program of the interacting electron molecules, solid liquid with exciting neurophenomena. It was recognized in the star quantum mechanism. That is many electron problem is more than hundreds years old problems. The more we try to improve on that function we want to approximate, the more we have better devices, the more we have what we can think of. Okay? The question is how can we understand and calculate the property of the it? And the major breakthrough was density functional theory. As I'm speaking now, you can imagine number of publications that are being published using these techniques for each year. So now, the many body problem present more challenges that are not answered by this theory. There is need for guiding principle to navigate these issues. So, a solid, this being a collection of supposed to be charged particle nuclei and lighter electrically charged particle electron. Already the system is in quantum mechanical many electron problem. Okay. So interaction. I already explained this. We have equation. We have kinetic energy of electron. We have potential. Plus includes some average interaction. Then we have energy eigenvalue values. Then we have the wave function. So we know electron, we can easily solve the equation. talk about this. Okay, now this is the condensed matter hydrogen I talked about in my summary slides. This is the kinetic energy operator of the nuclei of the electron, and this one with the Coulomb interaction of the nuclei and the electron, Coulomb interaction between electron and other electrons, and Coulomb interaction between electron, nuclei, and other nuclei. So, in my first slide, I removed this and this because nuclei is heavier than the electrons. So we end up having our Schrodinger equation in this term, kinetic energy operator, and we have this second term here, Coulomb interaction, and the last term is external coordination function. So now, the kinetic energy of the electron plus potential energy due to electron interaction. This is again the known potential energy of electron is the external potential of the system. So we end up having a Cauchy Hamiltonian, which is given by this relation. So now, two theorems, as I have stated before, two theorems. One is Hohenbach and Kohn. What he said that one of the important ideas in quantum physics and chemistry without any equation is this statement: unique fingerprint, correct electron density define everything about the system. That if you know an electron density defined by the system, and the guiding principle, that is the rule of finding the correct density map, just like I mentioned in the library analogy. Okay, which address the impossible task of tracking a single electron is to reduce to finding just one stable three-dimensional map. This insight is a foundation of DFT, the work of modern physics and material science. And it's like the foundation of how we simulate drugs, natural materials, solar cell, and computer without having to do impossibly complex calculations. Okay, now, just I mentioned this also that quantum mechanics is complete from political density alone. And energy is minimized with respect to density in order to obtain the ground state density and the energy. So what we don't know is the ground state energy and density of the energy, and we also don't know the potential. Okay. I talked about this before when I mentioned that this relation reduces the task of finding the ground state electron density in three-dimensional wave function. When you have one electron, you have three-dimensional matrix, right? If you have two, you have six, because each one has three vectors in space. So this equation actually helps us to now be able to consider a non-interacting pattern. This is the idea. Okay, so the real challenge of having typical electron is addressed. Now you just have the fictitious non-interacting electron. It doesn't exist. That's why they say that clever idea that what the Nobel Prize. It doesn't exist, but it's leaking way you can be able to map it to the wave function of the many electron system. So the big challenge is looking forward to do this, and this is why we have combination of getting three variables of ground state electron density instead of three variables of the wave function. So now electron structure program, if you look at this, we have Hamiltonian that contain kinetic energy of electron and the interactions, and we have electron in the external potential. So what DFT did, as I have mentioned, our team repeated this, is to have a O'Hare and Korn energy function that contain energy operator, and internal potential, and also the external potential. So we have energy functional as a function of breath. Once we say if you know the density, you know the energy potential about the system. So which is the O'Hare and Korn functional, this one, and which is proposed the external and Korn relation, where the functional of O'Hare and Korn is given by energy operator plus the internal energy operator plus nuclei interaction. Okay, so I've already mentioned that the ground state doesn't determine potential, and so the potential determines the density. However, there is no practical provision to calculate anything. It's just a statement. But all I shall provide this practical way, constructing an auxiliary system of non-interacting electrons. The good function that takes into account the effect of interaction in the actual system. This is clear. The heart rate energy and the external correlation energy. So the external correlation energy actually is exact for ground state and total energy of the interacting system. And the new variable is to find information for this external correlation function. And the good approximation requires information about the interacting new body problem. So this expression implies that ocean energy becomes a soluble problem. So all many body effects are included in the effective potential via the external correlation function. This is what I said before. We have a ocean effective potential that contains the real landscape and the Hartree Fock correlation and also the external correlation function. So writing the functional for auxiliary system of independent particles, the density is written as the sum over all single particle function. I have shown this in one of my slides. Only that this is not supposed to be. So we have now energy for independent particles. Then we have Hartree energy, so that we have the quotient energy given by these expressions. So the first four terms are soluble part of independent particle. The first four terms, 1, 2, 3, 4, they are soluble. The last term is the exact combination of an unknown functional. So we search for useful approximation for this. The search for this useful approximation for this extra energy as a function of electron is still on, just like I have mentioned. if you remember the lab analogy. So now we have potential energy can be minimized with constraint so that the function to be autonomous. So this leads to variation principle to the one electron function equation. And this equation you see here is one electron function equation where you have kinetic energy operator. PKS actually is the one that contains these three terms. Then you have take energy to the other side, you have A side of. So that's why I put this one to 0. So self consistent potential equation for independent electron with effective potential, whereby this is the effective potential, and this is defined here by these terms. Now, how can we simplify this exchange? The electrons, not independent, is another different part of the main body effect. Fortunately, for the ground state that is useful approach the exchange and correction mode, where we have exchange, which is exclusive principle. Just by analogy, you cannot have two inside the library. And you have correlation, is repulsive polymer interaction. Your behavior inside the library is defined by the people around you. You try to avoid collision with people around you. So we have now okay, maybe I'll go down here. This is one very important in this slide, that there are other advanced developmental positions. I have mentioned that here that not all systems can be handled by this exchange correlation function. We know this exchange correlation is just some small portion that each solves approximately, and you can plug it and define the total energy of your system, right? So unless you have it correct, it means the total energy of your system cannot be correct. And that total energy is actually what you use to determine other properties of the system equations. Okay, so now we have two approximations, LDA, my library analogy. So what is this LDA is all about? It's just we are trying to create the sound, considering taking the sound noise of each row. So you are just in vast approximation. This is the LGA, and this is the expression of the LDA. Why you have the ground state density, and this is what homogeneous extent and correlation function. And so for you to get better approximation, now you have to use EGA. If you go as maybe I will show in the next slide, not all material. This function is different from material. Some material you can handle with GGA, some you cannot. If you see LA, you will get better result. And this is actually why lies the difficulty of computational materials are. So trying to understand which skill you are going to use is actually very difficult. Sometimes you cannot even use this. We have electrons, and these electrons doesn't have any ID. It's not possible that electron will interact with electronic systems. So this is another correction. So we call it self-interaction error. You have to, if you have a very big system and you have this error, because skill is considered electronic interaction. So if electron is not possible to interact with the stage, so we have to remove that and self-interaction error. So it's beyond GGA and LGA. So we have expression for exchange. This is for exchange. This exchange can be solved. You can have an exact solution of the exchange. For the coordination, we cannot have. There is no analytical solution for coordination of homogeneous system. However, it can be obtained numerically for a number of places using accurate multiple calculation. Fitted to parameterize function of density, satisfying the high. While you have high density, you use action to be this much. Then of RS, where this R actually is what they call Woodlands is radius of your system. And where you have low density, you use EC to be this. As R approaching infinity, you have the external correlation to be O over RS plus B over R S on a 2 over 2. You can get actually this publication, all these values in publication. We intend to share all the PDF of this material. Okay, so the exchange, the GGA was developed to provide the quality of the result of LPA. So action and correlation energy is enhanced by modifying factor called FSC. We take care of the local variation of this. Just like what we used to do in the data analysis. If you want to get a final interested in good result, you make a final mesh so that you can be able to account able graduation in the density. So it's just like this multiplier of what it is doing. So many modern codes using DFT now use more advanced approximation to improve accuracy for certain properties. And there are actually different parameterization of GG. I have already started using Espresso. We are just familiar with PPE, the playable of GGA. Actually, there are actually so many of them. Each one has its own pros and cons. Okay, so other recent increased use of theory of differential system that incorporate other effects and treat excitation more accurately, improve result for transition, pressure, give price structure, etc. Note, all the steps are actually based on orbital question idea. Because orbital algebra and less. It was the Florida equation that posed these three solutions. So, sorry. I talked about some other functions. I'm not actually going into detail here. This is a slide by Timron Luri. I attended one training, so I know him. So actually, what I want to show here is basically some advanced function, also advanced formulation beyond HA and GGA. Like for example, this one is self-interaction problem. Of yourself, right? So we have to consider that. So due to approximation to the external correlation energy, each electron interact with only star. Actually, this is the approximation of external correlation, and this is not possible. Therefore, we just give an analogy. If you have cards written at the mirror, it will assume it's a like card. So what is happening is just what we call self-interaction corrections. So the dog doesn't realize it's biting. So this is another But this one actually is used for strongly correlated electrodes. When you have a system like say metal, nandrite, and actinide. So mostly, if you are familiar with nutrition, you find out that mostly people use what we call DFT crossing. That is correction you use on the orbital of the particular atom in our materials. Just to address this self-interaction, and it pays a lot. When you compare with other results, you find out that your result you got using this is very closely matching the experimental result. That is where you have the experimental result. Even though some people are using this you another element that are not traditional or life. Okay, so this is just about this self-interaction. This is advanced metal correlation. We have too much functions, DFT plus U, even more modified one is DFT plus U plus B. Then we have hybrids, E3 leaf, EPP0, SS06. This diagram, you have so many. So many that if you are want to study the system, you have to go to literature, look, understand what is the nature of your system, which one you are supposed to use for your own system. We have Vega, GGA, we have Banda correction, mostly for three-dimensional, two-dimensional materials, which is also is orbital specific. Also, if you want to do calculation, your material is two-dimensional material, then you have to incorporate these corrections. It also have many variables. Okay, this is just some of the example he gave us. Maybe I will read this one. Okay. We are not treating DFT process, so I'll just roll this and give you the presentation. Now, testing of DFT function and accuracy for transition items. So this one is just I try to put on to bring this up to you so that you have at least an idea of what is happening in the community. Function, arrow of theoretical lattice parameter for the large variety of solid, from lithium to rhodium. You can see these are different levels. LDA, M is mean arrow, MA is mean average arrow. So you can see the graph, the elements, and also the functions, and the margin, and the arrow bars. I think I have the link for this application. You can check it. Now, another example is polarity parameters that we want to discuss also here in DFT. So when you have polarity, you have this is experimental lattice. This is 3D element. You have PPE now is 0 to LDE, which is much smaller. You see, we have experiment 2.51, LDA is 2.42, PPE is 2.49. So you can say that, or if you have a system like this, say that PPE is better than LDA. For 4D elements, lithium to silver, you have experiment, you have WC to be better, LDA too small, PPE too large. So these are also being functional. Go and go ahead. And most of these functions actually are implemented in most of the report. So for 5D elements, LDA is 0, and you see, and PB is too large. So this is LPA. These are just to bring to our notice that before we start anything, some mistake, the time you spend to understand your system will be better than start doing raw calculation. Just computer code, whatever you can get on output. So this is very important to know what you are doing. I think this publication will take you to just next example of DFT calculations. One, properties of crystal whose properties are well established. I will tell you that I have solely resolved that match 100% with the survey. So it depends on who is doing the research and what is want to do. Okay, definitive test of theory comparison with experimental calculation for other more complex systems. Sometimes we have prediction comes before experiment. Maybe I have this example to show. Actually, this is what I was involved in before any publication in experiment. There has been, sorry, I'm just taking my time because I think this is just on the background. Sorry, I'm just on. So you can have prediction before experiment. This intermediate band for solar cell observation has been proposed. You know, you need a very good observer. You need a gap that is within the visible spectrum. So, but now the energies that are less than that gap will be wasted. So some people propose that even the energy less than that gap can be used to improve the solar observation. That is the idea of intermediate band solar cells. So you have intermediate energy levels between the overall band gap of the material. This is has been done and it has been shown to improve accuracy of absorption of solar cells. Then we have also some calculation surface interface, outline, instruction, looking, mentioning the structures in the environment, large complex molecular solution. This okay. This is okay. So I think this portion, then I will talk about now ensuring key point, lattice content, and agricultural convergence. But I will talk about this briefly. This because actually it's very important. Okay. So, common mistake you see, we see people are doing DFT approximate many body control problem. So, computational parameter include approximation, then we control K grids, cell size. So, comparison test is body process of this numerical points. So, one of the things we do to improve accuracy actually is this conversion test. You define the property of intraday conversion. Conversion is mean that at which one gives you the lowest gas energy, then that will be the parameter I'm going to use for the calculation other properties. So then we have the core concept. For example, K-point sampling, sampling electronic state in historical lattice. K-point conversion fundamental critical step. in accurate, reliable calculation of espresso or any plain way of, like maybe bars. The difference between bars and espresso is that in bars, the zero potential are nice. That's why mostly you get a better result using bar espresso. So it is a process of determining the number of K point sampling inside the first period zone, needed to accurately approximate the integral over the continuous electron, so that further increase their number does not significantly change the result. If your system is metallic, definitely it's going to use denser mesh. This we know. So you have to understand based on the system you are using, you have to find the K grid you are going to use for the conversion test. Okay? And for example, in an infrared perfect crystal, electronic states are labeled by continuous wave vector K in the EZ. So properties like total energy, electron density, and forces are calculated by integrating over all these K points. For example, electron density, since we cannot compute an infinite number of K points, we discretize the billions of using black mesh K point. This K is inspired espresso by K point. Okay. The fundamental problem, if the grid is too coarse, our sampling is poor, and the integral are inaccurate. If it's too dense, the calculation becomes expensive with unphysical result. So the conversion of K point directly controls the accuracy of almost every property we want to calculate. And unconverged lead to incorrect absolute energy differences or inaccurate process error, regularization, self-parameter, reduction of stable crystal pace, or electronic structure. So once you mess up from the conversion test, is whatever follows on is wrong. So computational efficiency, we have two false results are wrong due to waste computational resource because simulation is invalid. This is very common to students. I propose if you want to start, then start on this error. If you understand this, definitely you are going to get good result. Good result means good communications. Look, getting a very good communication is either advantage to researchers. If you get an offering, what they do is what you give. Good communication will attract LOTs. So, two dense calculation can increase dramatically using scaling linear variable or dramatically with number of K points. And during the waste of competition, so you will not include them. The goal is to find where the property of interest lies. Total energy for atom, one graph, changes by less than exclusion tolerance when the grid is further increased. So these are the factors also influencing K point convergence. So, for example, I mentioned metal requires denser mesh. Insulators or semiconductor combined will get to pure K point because there is an energy gap. System size also determine large huge cells have smaller brain zone. Therefore, they often require a coarse K grid or even only one gamma port. Likewise, if you are treating a two-dimensional, so you don't need to satisfy any grid on the y-axis of your material. Okay? Systems property of interest, total energy might convert with boundary grid, forces and dielectric properties or cross binding and even denser grid or separate non-consistent calculation, much finite grid NSSP calculation which is foil. K-point conversion Espresso, this is some standard procedure, maybe we can the answer. Now we have also lattice constant conversions, finding the crystal recurrent geometry, total energy of cell volume, lattice parameter, if it is cubic. The minimum energy can give recurrent geometry predicted by identity and accurately relating this minimum. So why lattice conversion is very important? Band gap and dispersion energy change with bond elements. Vibration properties one frequency are extremely sensitive. So wrong lattice implies imaginary or unstable forms. Lattice electric properties like wrong modules come directly from EV car. So if you mess up from the lattice, convergence may not be able to determine correct wrong modules reality. Phase stability of energy different phase is actually meaningless unless each is at its own equivalent volume. So note, the calculator lattice concept is the best check against experimental data. Last point, validate your control potential for functional choice. I'm just rounding off. Okay, no problem. It's supposed to be a link to just give an example of maybe needs. Just begin and show this one. That is one thing I just want to show here. This is example like this. I just finished talking about K-point. That is the first thing you compare. You compare, don't compare what you have with the experiment. If you want value that is matching the experiment, it means that you are good to go. You use that particular structure and give that for calculation. Just like this, you have theory, you have experiment, and with these parameters, lattice constant, volume, and other parameters. So it's very, very important before you start, you do this conversion test and compare with the experiment before you proceed. I'm very sorry, my slide doesn't contain the last slides. So please come the end of my presentation of. Thank you so much.
Thank you very much, Lawal Muhammad, for this wonderful session, introduction and brief history of functional theory. With this, we are going to have a 15-minute tea break, after which we will come right back here and start the hands-on session. Maybe we will take questions during the hands-on. Let's go for the tea break. Immediately when we come back, before we start hands-on, if there's any question, you can ask regarding this session. Lawal will be much available to address some of our questions. Thank you. The tea is available at the back. We can start going and have it the next 15 minutes. Okay. So, for the tea break, some of us that are from ABU, courtesy demand that we allow our external participants go and get their tea first, then we follow them. Is our student, let's be patient, please. Eh?
You have succeeded in confusing us. DFT. How is it? Overloaded us. Overloaded us, and you have succeeded in confusing us. By the time we realize you understand something, you just come and take it. The good thing there will be wannan ya kamata ya tsaya ba. Ina sai da yake tsaya wani ne.